All right, hello, welcome back. This is Mr. Maze coming you through the virtual, brilliant Digiverse. And today we're going to be taking a look at some of the big notes that we need to understand when we're talking about z-scores and percentiles, and basically understanding how to visualize data and to mess about with quantitative data and spread and value under a curve, so density of values. So you can see right here, just like in class, I want you to take a look and have access to this particular slide here, where we go through and we learn how to use normal CDF. Now, the two ways you might use normal CDF would be either because you want to turn a z-score into a percentile, or because you want to turn a data point into a percentile. And that should make good sense to you. So what you're going to do is you'll do second vars, and you can see where that's highlighted on the picture that you're looking at. And I go down to the second one. You can probably hear the clicking of my TI-84 alongside yours. So we're rolling in tandem. And I click enter. There's an opportunity for a lower bound. Now, something I talked about in class is you will either make the lower bound a really, really, really low negative number. So in the case I offer here, negative 100,000 works. Remember to press the negative button. That's the one in the lower right below answer, not the minus button, because the calculator will take a giant sad dump all over both of us if we use the negative. It will say there's an error, but there is, of course, no error. The error is simply that we didn't use the negative. So we will do negative 100,000. But remember, when we do that, when we set the lower end to a really, really, really negative number, what we're essentially doing is we're saying, I want to find all the values smaller than my upper limit. And my upper limit in this case will be either my data point, if I'm trying to find the percentile from a data point, or it will be my z-score. And so what that's effectively doing on our beautiful normal curve is it's taking that data point as it lies on that normal curve and saying, give me all the values going all the way back to negative 100,000, which is basically all of them, right? So you might set an upper limit that's a data point, and then you would, of course, if it's a data point for the upper limit, you would then change your standard deviation. So right now I'm plugging in an upper limit. I just picked 60 randomly. Of course, that would be a real data point in a real question, and we'll practice that with later problems. But you would put that data point in. You would then change the mean from 0 to whatever mean I've given you in the problem. You would then do the same with the standard deviation. You would change it to whatever the real standard deviation is in the problem and not the number 1. And then you will click paste, and then you will click enter, and that will give you a value for your percentile for that data point. Now, if you want to do it with a z-score, you do the same thing. But of course, instead of putting in the upper as a data point, you'll put in the z-score, and you will keep, or you will put in 0 for the mean, because all z-score related standard normal curves are mean of 0. And you will put in a 1 for the standard deviation, because again, similarly, all normal curves that we have set to the z-score standard, which means it's uniform across all values, we would then set to 1, right? Well, I should say uniform across all different normal curves. That is, it's something that's equivalent for each normal curve, which is part of what makes z-scores so brilliant. And you'll do the same thing. You click paste and you click enter and you get your values. And all of that, of course, is here. Be aware, though, as I said in class, you may make your lower into your z-score. And if you do that, you would want to make your upper into positive 100,000. And the same thing is true. You may want to make your lower into a data point and then your upper into 100,000. And that's if you want to find all of the values that are greater than your data point or greater than your z-score. Okay, that's been plenty of looking at the same picture for a while. I know you want to see my drawing soon. Worry not, we are getting there. The other thing that we did in class was sometimes we want to take a percentile and we want to find the z-score that's associated with it. Or indeed, we want to find the particular data point that's associated with it. So for that, of course, as it says in these directions, you'll do second vars. You'll go down 3 to inv norm, which is invert norm. So that's option 3 under distribution. Click enter. And similarly, you will find yourself in a brilliant situation. And that brilliant situation is as follows. You will see area. And area is super important. Area is your percentile that you are converting. But remember, for area, we put in a decimal, not a percentile. So if it's the 33rd percentile, that is 0.33. If it is the 5th percentile, that is 0.05. And that's what you'll put in for your area. You will then, if you want a z-score, again, you will use 0 for mean, and you will use 1 for standard deviation for all the reasons we said. And if you want to get the actual data point, you will put, once again, the mean that I give you in the problem for the mean and the standard deviation offered to you in for the standard deviation. You'll go down, you'll click paste, you'll click enter, and lo and behold, you will get a beautiful either z-score or data point value. And there you go. So something I want to make very clear is that all of these calculations, these two that we've got alongside, I'm actually going to scroll down, we're going to switch to drawing for a moment. All of those two calculator calculations, the way they function, and this beautiful equation that we've used in the past already, all three of these tools in your proverbial tool belt are ways for you to take various problems and find solutions to them. So don't feel like there's like a memorize heavy way to do this. Get comfortable with using these in various ways. And that's what we're going to do. All of the practice problems for this unit assessment are different ways for you to toy with these tools so that you can more fervently understand how to find solutions. And that's the exciting part. Some of these are going to be very puzzle heavy, and you're going to have to think critically to find solutions. The last thing you should be able to do is understand this normal curve here. You can see how I've shown you the way normal distributions function in terms of percentiles setting up. Remember, of course, that the center is the mean, but of course the 50th percentile, and I've said this many times in class, is always the median, okay? Now, in this beautiful, and the reason why we say that is the median will always be the 50th percentile. The mean is always reaching toward that value, especially in normal curves. We are working toward that reality where the mean, median, mode are all the same. And as we know, skews can impact various things. I will come back to that, of course, though, at the end of this lecture. Okay, so I want to work through a particular problem. You will notice, actually, a side note, I just want to be very clear about this. You see here how it says like mean plus standard deviation, mean minus standard deviation, and so on at the bottom on the x-axis. You need only put like negative standard deviation, -2 standard deviation, -3, or positive standard deviation, +2, +3 when you're making your sketches. And this is just a good rule to know, okay? This is known as the empirical rule. This image here, where we have our 234s within 1 standard deviation, our 13.5% added on the sides to get to 2 standard deviations on either side, 2.35 on either side to get to 3, and so on. Okay, we've done our sort of homework, we've eaten our Wheaties, as they say, and now we're going to look at a problem. So if you will, do me a huge favor, pull up your slideshow that accompanies this. It should be up on Canvas. It should say 1.6, normal distribution calculations for Mays. And go to slide 9, and you'll see it says classwork problem 1. And we did this one in class, but I really want to go through it really quickly with you. This is how I might answer this one question in a way that is super thorough. It says the distribution of heights in Mr. Mays' class, which I calculated, of course, using your data, has a mean, and I'm already going to write this down, of 68. We also see that it has a standard deviation of 3.66. Lovely day. I'm then asking, what is the percentage of people whose heights are greater than 72 inches tall? Okay, so now we're asking ourselves, well, what am I going to do? Well, there are a few ways I could go about solving this problem, but I want to use the calculator for this one because I want to show you guys how I expect you to notate the calculator work you do. Because, of course, neither I nor the AP people know what you're clicking into your calculator. So it's time to divulge your magic to them, okay? So the first thing I'm going to do is I'm going to pull up normal CDF. So that's second vars, and go down to the second option. And actually, when I'm giving my answer, I'm going to put my answer in green. I will write normal CDF. And that's just the first part of my answer. I'm like, whoa, AP graders and Mr. Mays. That's where I started. Now, I'm realizing here that this is a problem that's asking for the values that are greater than 72 inches tall. So for those of you who have got your mind sharpened and at the ready, you know that my lower bound is going to be my data point here because I want to find everything up to a very high upper bound, which is sort of infinite, right? We want to find the higher values. So the low end of my higher values will be 72. So I will put 72 in for lower. My upper, I will do 100,000, as we said before. And I will write that down in my answer. Lower, you can hear me clicking it in my calculator. Lower will be 72. Upper will be 100,000. And then for my mean, mind you, I have put a data point in. So I'm not going to do 0 for my mean. No. That would be simply untenable, senseless of me to do that. No. Instead, what I'm going to do for that, I'm going to put in my mean, which is 68 in this case. Absolutely wonderful as that is. And then we have our standard deviation, which is provided in the problem. It is 3.66. Beautiful. So I'm going to throw those in, 68 and 3.66. I'm going to go down to paste. I'm going to click enter and enter again. And of course, I get my value. That value is 0.137. Okay. And then because we're asking specifically per percentile, I'm going to then multiply that value by 100 to get percentile. And that gives me 13.7%. Now I'm almost done. The final part of my solution is 2 parts. One, I will say 13.7% of values are heights greater than 72 inches. Now you could say that a bunch of different ways, but I think the idea is pretty clear here, right? 13.7% of values are heights greater than 72 inches. Okay, the final thing I will then want to do in a solution like this is I will want to draw a little curve. So I'll do my cute little curve. This is a relatively normal curve. And the good news is yours cannot be as hideous as mine is. Actually, I'm not even going to bother drawing the y-axis. Who needs it? And actually, let me try to make this just a little cuter for you because you deserve the best. Okay, boom. Okay, that's a little better. Okay, and so just like with my other setup, I'm going to make, and actually I'll do this in a different color so it's a little easier to see. I'm going to do it in black here. I'm going to set up my mean. It's going to be right down the center. I'm going to do the signal that it's my mean. And then, of course, I'm going to write 68 below it because that's the value. Okay. Now, standard deviations are exactly that, standardized, which means they will be approximately the same distance apart from one another on my sketch. And I will put them in as negative standard deviation and positive standard deviation. I will then do -2 standard deviation and +2 standard deviation. And this is just a mimicry of what I might expect you to do in your answer. Now, you only have to go as many standard deviations out as is relevant to your data. And we will see in a second what that looks like. Now, I'm going to put the values in as well. Because I know my standard deviation, right, is 3.66, I just have to add 3.66 to 68 to get my first standard deviation, right? So that gives me 71.66 for my first standard deviation. And you'll have your calculator on you, so I'm going to add 3.66 once again to 71.66, and that gets me to my next standard deviation 2, which is 75.32. Okay? Those are my values. Now, already I can see that my data point, right, is 72 inches and higher, and I know that's between now 1 and 2 standard deviations, so I'm going to be able to stop here and color in the rest, right? And of course, my previous values I will put in as well. 68 minus 3.66 gives me 64.34, which will be this. And then once again, minus 3.66 gives me 60.68. Now I'm doing a little overkill here, but it's beautiful for that reason. We've got all our values in, we've got everything sitting the way we want it to, and the final part is shading, which I can do a great job of now. I'm going to do in red, actually. I'm going to set vaguely where my line would be. Now, I know it's at 72 inches, so I'm going to set it just after my first standard deviation of 71. I'm going to set that at 72 inches. And then I'm going to go over to my red highlighter, and I will simply highlight the area coming after that. Boom. And yours will be cuter than mine. You'll notice, actually, I don't really like the way, yeah, let me get rid of that little bit there. I want to make sure it's more centric to what I was trying to go for. If I can get it. Yeah, there we go. I'm an artist. Beautiful. And so that would be the area that is greater. And the last thing you will do is you'll put a little key here. I love to put these in. It makes it really easy for AP graders to read. You'll do capital N, meaning this is a normal curve, parentheses, and then the structure is mean, which in this case is 68, comma standard deviation, which is 3.66. Now, a little overkill, but that is what an answer might look like. And you will be so impressed with yourself and very happy to know that despite the fact that the problems are getting more and more complicated, or we're toying with different ways of doing things, anytime you have a problem where you need to sketch a curve, it will look something like this. We've done it. We've done the majority of the hard work. So take a deep breath with me. Congratulations. I hope that makes good sense. Okay. We've done our wondrous due. Let us move ever forward. And let's try one more thing. Let's try the 68, 95, 99.7 rule. That's what it's called. It's called the 68, 95, 99.7 rule. In case you are interested, if you see that, that's what this is. It's a rule. Now, it's a pretty simple rule. Now, if you're on slide 13 of the PowerPoint slides, you'll see the definition there, so you can pull from that. But basically, it's that your min and max, in order for something to be considered normal, in order for a curve to be considered normal, your min must sit between -2 standard deviations and -3 standard deviations from the mean. So standard deviations to the left. It must sit between those values. It can be -2 standard deviations. It can be -3. It can be no more, though, than -3 and no less than -2. Now, for your max, the same rule applies, but in opposition. So it's got to be between 2 standard deviations and 3 standard deviations from the mean, okay? And so as you can tell, if you go up to slide 14, we have this huge data set where we have a bunch of values, but we did this in class, and what we remembered was they gave us our mean for that distribution, right? It was 77.7 points. They gave us our standard deviation. It was 8.44. And they said, hey, is this an approximately normal curve using the rule that I just taught you? And they give us all these data points, but you'll notice data point 1 is actually the min. And the min is equal to 57. And data point 20 is the max. And that data point is wondrously 94. Okay? So we have our min and we have our max. Now, you probably already understand where I'm going with this, but what we want to do is we want to take our mean, which is 77.7, and we want to add 8.44 to it twice, because we want to go, I'm going to start by testing the max. We want to go 2 standard deviations from the max there. So mean plus 2 standard deviations. I'll go to my calculator. I'll go do 77.7 plus 8.44 plus 8.44. And that gives me 94.58. Now, wonderfully, because I wanted to give us an easy one, we've already finished the problem because our rule has been broken. 2 standard deviations from the mean here is at least 94.58. But my max, as we see over here, is 94, which is lower than 94.58, which means my maximum for this graph is sitting somewhere here. If this were a curve, my max is sitting here, which means the curve is actually like this. And therefore, it is not normal. Now, if that value worked out, you would then have to test 3 standard deviations from the mean and make sure that your max is lower than that, but higher than 2. And then again, if that proved to be true, you would then want to test the min and see that it is lower than -2 and higher than -3. Be aware that sometimes I'll only give you a min or a max, and that means you need to check that min or that max against the value and be able to show, hey, this is normal or this seems normal, right? So if it follows the rules, but you only have the min or you only have the max, you can say this may be approximately normal because, right, we're in a situation where the max follows the rule or the min follows the rule, but we do not know if the other side follows the rule. But I'll just warn you, more often than not, what you'll get is a situation where, hey, indeed, one thing fails the rule, and they just want you to be able to say, hey, or I just want you to be able to say, hey, I did the 68, 95, 99.7 rule, and I found that the problem was my value, like this one, was actually between 1 standard deviation and 2 standard deviations from the mean instead of being higher. All right, we learned a new rule. Let's roll ever forward. You'll see on slide 15, I'm just reiterating again, make sure to sketch your graphs whenever possible, your curves, and now you know the rules of what a curve should look like when you sketch it. It should look like this one. All right, and let's really quickly do classwork problem number 2. This is a really, really, really good one to get your head on straight about sketching curves. That is on slide 16, so if you'll join me on slide 16. There are 3 parts to this question. We'll call them A, B, and C, right? Now, part A, I'm not going to spend too much time on, but we have a problem where it says, hey, the heights of adult women are approximately normally distributed. They've told us, so we don't have to check, with a mean of 64.5 inches and a standard deviation of 2.5 inches. First it says, sketch the normal density curve. What does that mean? That's A. We'll call that A. And it's very simple. You do a normal distribution, you set your Y, and then, of course, you'll set up your mean. This is just without any utility. We just set up the value, and then we set up our deviations, negative, positive, -2. You can see how fast I've gotten with these. I know it's hideous, but part of why I'm so fast with them is because, like you soon will be, I've done this so many times, it just becomes second nature, right? And then, of course, if you want to put the particular values, you will then subtract, so this will be 62 if you go down 2.5, and then it'll be 59.5, and so on and so forth. And then this will be 67 and 69.5. Okay. We have it, and then, of course, we will do our little key. We'll do n, right, 64.5, 2.5. Because we're legends. That's a point, not a minus. Okay, we've got that. That's part A. Part B in particular, I'm going to need more space. Part B is asking for something special. Part B says, what percent of heights are greater than 69.5 inches? Now, we already did an example of this right up here, where we found heights that were higher than 72. So that should feel pretty good. I'm going to give us a check mark on step B. But suffice to say, you will do the same process you did with this problem with 72 as our height, and you will show me all of the work that we did here for that one. So I want you to try that out on your own and see if you feel comfortable with it. What I am going to do is part C, we will call it. Part C is what percent of values are between 59.5 and 67 inches. Now, I want to start by saying if you take a look at these two values, I'm going to put the and there. If you look at these two values, you'll see they actually hit -2 standard deviations from the mean and 1 standard deviation from the mean. So you could go look back at your gorgeous normal curve and say, well, we're going from -2 up 13.5%, right? Up 34%, up 34%, up another 13.5%, and suddenly we are rolling. Well, actually, wait, it's 1 standard deviation, so it's 34 plus 34 plus 13.5 approximately. So that's 68, 78, 81.5 approximately, right? And that's one way to do it. You could use your empirical rule to do that. But let's say for the sake of argument, you don't get two values that are, exactly at standard deviation marks. And you need to solve this using your calculator. Allow me to walk you through that process. We're going to get a tiny bit of a difference in our answer because it's more precise. And that's okay. AP graders are not looking for exact answers. They're looking for answers that show process. So I'm going to show us how to find distribution values between two values. Okay. Now, there are a couple of ways you can do this. Option 1 is you can find the percentile of each of these values, and then you can subtract the bigger one or the smaller one from the bigger one. So you could take your 67-inch percentile, and you could take your 59.5-inch percentile, and you could subtract the 59.5-inch percentile from the 67-inch percentile. And to do that, you would go second VARS, as you know, you'd go normal CDF. You would then make your lower something really low, negative 100,000. You'd plug in your upper is 67 inches, and you'd put in our mean and our standard deviation, and that would give you your 67-inch percentile. You'd do the same for 59.5-inch percentile. You'd subtract and you'd find your value. But I'm going to show you the fun way to do it. The fun way to do it, as we learned in class, is set your lower value as 59.5, right? Because that's your lower side of this particular distribution set that we want to understand. Set your upper to 67 inches. Beautiful. Now your mean is going to be 64.5 because that's the mean that was provided to us in this question. So 64.5. And your standard deviation is going to be 2.5. You'll go down to paste and you'll click enter. And lo and behold, you will find very close to the value we approximated ourselves. You will find 0.8185. which is approximately 0.82, which will amount in percentile to 82%. Okay. And that means that 82% of our results are sitting between these values. And again, that should make sense because even though that sounds like a lot, if we take a look at our normal curve, it turns out that's actually a huge chunk of our data is sitting in that particular spot when we did our math over there. Okay. That's beautiful, wonderful, etc. Bob is your proverbial uncle. But I need to know something else. There's something really important here that I haven't thought to put to words. And that is, why didn't I show my process? Mr. Mays, you fool. How could you have done this? It's okay. We're going to do it right now. We're going to write down what we did. We did normal CDF, right? We went in, we set our lower to 59.5. And you'll be doing this work yourself. We set our upper to 67. We set our mean to 64.5. We set our standard deviation to 2.5. And then we got our value up here doing that math. And the last thing we would say is 82%. And in this case of heights, sit between 59.5 and 67 inches. And the last step after that is we will do our little graph. And for the sake of this speedy roll, I will just use the graph I made here. It works great. The only thing I have to do to make it really effective is I'm going to use blue to do this part. We're going to go to blue. Excuse me. Okay, and we will say we were going between 67 and 69.5. Those are my two values. And then I will get my highlighter and I will highlight all of the area under that part of the curve. There we go. And that, along with all of this, makes up my beautiful, lovely, gorgeous answer. And that's how I'll answer problems like that. Okay, really quickly, we are going to roll through some transformations, and then I will leave you to your brilliant devices in solving further classwork problems that sit in this problem set. I also want to go over a couple of quick tips for the unit test in this video. Be posted for tomorrow's video that I'm going to throw up where I solve questions 1 through 4 at the very end of this slideshow that you're using for reference, this 1.6 slideshow. Okay, but let's look at transformation problems. So if you quickly slide over to slide 17, we're going to do our transformation problem that we went over in class. We have this situation where we have a researcher and he's testing toxicity in blood. And the situation is pretty wonderful. He wants to make his data easier to read and easier to understand. Okay. Now, normally it says he has a mean of 8 and a standard deviation of 2. But the researcher determines, I would argue wisely, we'll say that's old, right? The researcher determines rather wisely that it would be better if he could set up the mean to be 50 and the standard deviation to be 10. And that would be an easier graph to read. Now, the wonderful thing about normal curves is we can make these kinds of adjustments without compromising the data. It's adjusting the data, but again, this is just going to make it into a more gorgeous, easily visualizable distribution. It will not fudge the actual value of that distribution because everything changes relative to each other, so that makes it beautifully fair. And this should click in your head. This is the wonder of these kinds of graphs and these tools I'm giving to you is we're learning ways to toy with data that are safe, that are not you lying to the public, right? These are ways you can tweak data. Okay. So this is the way I would show myself solving a particular problem. The way they set this problem up is they say, well, I want you to imagine, given this idea that we have the new scores, whether that's the mean or the standard deviation, is equal to A plus B times the old score, where A is a value we are adding or subtracting from our mean or standard deviation, and B is a value we are multiplying times our mean or standard deviation. It says, what will the values of A and B be to transform these results? And this is the way I go about this problem. You will remember, and this is an important thing to remember, that when we do transformations, the center, which in this case is our mean, is affected by addition, subtraction, and multiplication, division, right? On the other hand, our guy spread, aka standard deviation, range, things of that nature, is only influenced by multiplication and division. So we're going to start with him because his changes are very particular. They can only be done one way. And then once we see how that impacts our mean, we will adjust the mean accordingly. So the way we would start is by setting up the following idea. We know new score equals A plus B old score, but because A can't impact our standard deviation, we should say new standard deviation, that's supposed to be my little blueberry, equals B times old standard deviation. And this should make good sense, right? Because we don't have to worry about whatever A is for standard deviation. It won't impact our standard deviation. And now we just solve this. Our new standard deviation is 50. So 50 equals B times our old standard deviation. Oh, sorry, 50. My goodness, I just used the mean as the standard deviation. I hope you were shouting at me, Mr. Mays, no, a terrible mistake you've made. And indeed I have. Let's try again. Our new standard deviation is 10, so 10, equals B times our old standard deviation, 2. And then we will divide by 2 on both sides, and we will find that B is equal to 5. Wonderful. So we found B. This is step 1 of the work we must show. Step 2 is now we have to plug B in. We will say now new mean is equal to A plus B times old mean. And you'll realize, oh, obviously, because the mean is impacted by addition, subtraction, and multiplication, division, I have to put the A in there for this one. But luckily, we have a new mean. That one is actually 50. Equals A, which we don't know yet, plus B we have now is 5. It's this guy over here that we brought on over. And then we have our old mean, which is 8. So 8 times 5 is 40. We have 40 plus A equals 50. And then we just subtract 40 from both sides. And we will find that A is equal to 10. So lo and behold, we have solved our problem. A is going to be equal to 10. B is equal to 5. And if it asks what will the values in A and B transform the results into, we will add 10 to all data and multiply all data by a value of 5. Boom, done. And we've done it. We've transformed our data. So be sure to understand that, to look through it. There are a lot of ways you can show me that you have done this process. You don't have to map it out exactly as I've mapped it out, but make sure you show all the steps of the math to get me there so that I, as a grader, can understand how you got the answer and see that it is effectively correct. This is just the way I've mapped it out to make it utterly clear for any grader. Okay, if you have any questions about anything we've covered, please do find me. There's one more thing I need to tell you, and it is very important. It is a list of different things that I want you to have kind of in the back of your head as we move toward this exam. First of all, remember to sketch your normal curves for various problems anytime you must or you can. Remember to label them effectively with your mean, your standard deviations, and this sort of mean standard deviation naming device, as well as your lines, etc., and your shading. Be sure to show all calculator steps when solving a problem. Make sure to think critically about your problems and don't freak. Make sure to go back and review old stuff like median and quartiles and data distributions for medians so that you feel comfortable with that alongside all of this new mean stuff. A couple of other rules. Remember. These are things I want to throw in for the test that you remember. Median is never, ever an average. We do not say the median is an average. That's the mean that's an average. The median is never an average of anything. Okay, it is the middle. That's what the median is. The median is always the middle. So the median is the 50th percentile, always. It is the middle of the distribution. The mean can be slightly to one side or the other, right? It's not always exactly in the center. It's as close to the center as we can believe, but the median must be by its very nature in the center, right? Remember also that if you see a left skew and a median, right, in a graph, think of it in terms of a box plot. So if I have a problem, multiple choice problem, and they're like, imagine a graph is left skewed and has a median blah, what's it going to look like? Maybe sketch up, instead of a histogram in your head or a curve, maybe sketch up a box plot where you're like, ooh, a left skewed situation. Ooh, you can see my Chinese language learning has alerted me to something. Okay, we have this conception, and remember to think of that and be like, oh wow, so that's where my values sit, and this is where this is how spread out, right? My second quartile is, so my first quartile to my median, which is my second quartile, or the second 25% of my results. Remember also that each part of a box plot holds 25% of all data. You're like, Mr. Mays, I don't understand. Why are you bringing this up now? Well, obviously, it's to prepare you for this upcoming unit assessment. So I'm just calling back some old knowledge because I want to toss it your way. So just like we have learned how to toy with means and standard deviations and use these tools in problem-solving clever ways, don't forget your old tools and how to problem solve with them. You will need them to decipher the multiple choice questions on this unit assessment. So be sure you feel agile with those, okay? I will go over and have gone over, I believe, in your class, one of the AP problems with you, but do come during office hours to practice those with me or ask any questions. Like I said, questions 1 through 4 at the very end of the slideshow, I will put together in a separate video. 2 more things I want you to know. Make sure to know your skews and make sure to know how skews affect data. Right? So all the stuff where it's like, where does the mean sit? We have the median here, and in a left skew, the mean gets pulled slightly down by the skew, the tail, and so on and so forth. And then the opposite, right? The median will be lower than the mean for a right skew. And know how that will impact data results when values are here on your x-axis. Interpreting things is just as important as memorizing things. Obviously, it's more important for this class, but you need the memorization to work through things. And the last thing I want you to know, histograms are sometimes given quartiles. So I was asked a brilliant question in class, probably a week or 2 ago, by a student, where they said, with a histogram, how do we know if it's an outlier? Well, what you would do if I give you quartiles, a quartile 1 and a quartile 3, is you would actually do that quartile test where you do quartile 3 minus quartile 1, your interquartile range. If I give you these values for a histogram, right? You would find that. You would multiply 1.5 times the IQR. You would then add it to quartile 3 and then subtract it from quartile 1. And for this approximate graph that I've done, you might even find, weirdly enough, that this point and this point are too high up and that they are outliers. So this is something I want you to have in the back of your head, is if I ever give you quartiles and I ask about outliers, the second you see quartiles and you see outlier as a question, do the math to figure it out, okay? And lastly, you may remember that histograms have bins, so they're not exact. Be aware also, though, when histograms are measuring full values of things, like children, how many children you have. I know that this is only values of 8. I know that this is only values of 10, for example. So in this case, I could tell you exactly how many outliers there are. If both of these prove to be outliers, I know if the frequency here is 1, right, and this is 2, and so on, 3, I know that there are 2 outliers, 1 sitting at 8 and 1 sitting at 10. Okay, I hope that has made sense. These are my little tips for you as we move closer and closer to the unit assessment. I hope this has been helpful. Again, we've gone through and reviewed some old stuff about medians and their placement and box plots and skew. We also went through and we looked at shifting data and how we present that value and what a word problem for shifting data might look like. We've mathed out some old and new means in doing that. We also did a great job of solving values where it's between 2 data points, and we have found the percentile there. We've shown our work using norm CDF. We've also shown our work with an answer and with a beautiful little sketched graph. Remember, if you are not doing norm CDF, if you're doing invert CDF, invert norm, I should say, it's the same idea for how you show your work. You do invert norm, and then you would do area, and you put in the whatever value you put, your proportion. So let's say 0.23, for example. I'm just picking one, right? And then, of course, as we all know, I'm even clicking it now to show, you would then put your mean in and then your standard deviation. In this case, I'm going to do 0, 1, so this would be a z-score, and I would show my work. So that's how I would do that if it were an invert norm problem. And then we've gone through and we've looked at how we can tell if something is normal by testing the min and the max between 2 and 3 standard deviations on either end. That's called the 68, 95, 99.7 rule. We then did another cube calculation where we calculated a percentile and looked for values higher than it using a data point. We also practiced doing that with z-scores and getting comfortable with that idea, and we got very comfortable with how we label our little sketches and graphs, another practice on our norm CDF. We got comfortable with this tool, z equals x minus mean over standard deviation. We looked at the empirical rule and its distribution of data for an approximation so we can solve problems, and we got comfy with our calculators. That's been a lot. You are all heroes. I adore you from the bottom of my heart. I look forward to giving you some more solutions to some of the problems that we have at the end of the slideshow. And if I get any popular requests, I may even put up a video this weekend with solutions to problems for you. But when we get back on either Monday or Tuesday, depending on when I have you, that'll be our review day. And on that review day, I always leave time for you to ask me more questions or to solve problems. You've been heroes. You're the best. This is Mr. Mays signing out.